next section is evaluating limits. So I'll start off by just pointing out working with the definition is not very fun. So luckily there are a lot of rules that you can use. I'm just pretty much here just going to try and list them off. These slides are more meant to be a reference. You probably would be able to find these. You know, I just Google for stuff most of the time. But it would be in the first year calculus textbook. I think that's where I found most of these rules. So I'm going to suppose that C is a real valued constant and that the limits as x goes to a of f of x and as x goes to a of g of x both exist. So they don't necessarily need to be finite, but they need to be something that I can make sense of. So they can't be 0 divided by 0, infinity divided by 0, infinity divided by infinity, things like that. Then, so we have a linearity property. So if I have a function that I can see is made up of two sub-functions, so f of x plus g of x, and I'm looking at the limit of that, then the limit of a sum is equal to the sum of the limits. Similarly, if I scale my function, so here my function is f of x, I'm going to multiply that by my constant c. So c could be anything. It could, if I want to double the function, it would be 2f of x, and so on. The limit as x goes to a of c times f of x is just c times the limit of c times the limit of f of x as x goes to a. So I think most of these are pretty intuitive, but they're all things that are proved in a calculus textbook, so you can use them. The limit of a product, the limit as x goes to a of f of x times g of x is equal to the product of the limits. So here I have the limit of f of x as x goes to a and the limit of g of x as x goes to a. And I'm going to multiply those two numbers together, and that's going to be the same as the limit of the product of these functions going when as x goes to a. Also works for rational functions. So the limit as x goes to a of f of x divided by g of x is just going to be equal to the limit of f of x divided by the limit of g of x as x goes to a. We have to make one little caveat here. So the limit as x goes to a of g of x can't be equal to 0. And then finally, we have the limit as x goes to a. So if I have any root of a function, I can put the limit inside that root as well. So here, this little thing here is an n. So if it was square root, that would be a 2. 3 would be a cube root, and so on. And then if p of x and q of x are polynomials, and c is a real constant that's greater than 1. So by polynomial, I just mean this is equal to something like p of x would be ax squared plus bx plus c. But it can be arbitrarily large order. So the first one could be x to the 1,000 or something like that. Then the limit as x goes to infinity of any polynomial divided by c to the x. And I could also write that as the limit of any polynomial times c to the negative x is going to be equal to 0. So it doesn't matter how big the order of this polynomial is, even if I have x to the 1,000. If I'm dividing it by a constant raised to some power, that's eventually going to go to 0. And then kind of a similar result, if I take the log of the absolute value, so I need the absolute value just because of how log is defined. It's not going to work very well if I give it a negative number. The log of any polynomial divided by any polynomial, if I take the limit as x goes to infinity, that's also going to be 0. And so just some examples. If I had x squared times e to the minus x x squared is something that would grow arbitrarily large as x goes to infinity, but e to the minus x is something that's going to be getting smaller as x goes to infinity. But because this part of the product has the x in the exponent, but here it's in the base, this term is going to dominate, and so the limit is going to go to 0. And then as an example of the second result, if I have the log of x cubed, and here the cubed doesn't really matter. I put any power here. I could put 1,000, 10,000. Eventually, as x goes, as x gets large, as x goes to infinity, this x in the denominator is going to dominate because of the logarithm on the top here, and this limit will go to 0. Then I'm going to add a little bit more notation. So if I, instead of using my arrow, my goes to arrow, as just a horizontal arrow, so that means goes to a value, but I don't care how I get there. I just have to be getting closer, but I could be bouncing from side to side if I wanted to get there. If I use this down arrow, I'm going to mean that x goes to 0 with x always being greater than 0. So it can bounce around a little bit, but I'm starting only on one side of the value and moving towards my limiting point from only one side. And then also, just in case you've never seen this notation before, the k followed by an exclamation point is read k factorial. And it just means k times k minus 1. Sorry, it's defined for integer values, positive integer values of k. It means k times k minus 1 times k minus 2, and so on, times 2 times 1. And then 1 factorial and 0 factorial are both equal to 1. And then again, we'll let c be a positive constant. Then if I look at c to the 1 over x, so you can sort of think of kind of intuitively what's going to happen here. 1 over x, as x gets large, is going to get closer and closer to 0. And c to a 0 should be anything to the 0 power should be 1. So it makes sense that this function, its limit, should be going to 1. Also, x to the 1 over x. So even if my base is getting bigger linearly, the limit of this as x goes to infinity is still going to be equal to 1. And then if x goes down to 0, x to the x power, this limit is also equal to 1. If k is a positive integer, and if c is greater than 0, or c greater than 0 is a positive constant, then k to the 1 over k, so this is just the same thing as a in the second bullet point, just re-expressed using integers. So the only difference between the second set and the top set is just now I'm sort of restricting k to be integer values. So it makes sense that we would get the same sort of result that we got above. And then also here we now have a constant to the kth power divided by k factorial. And the limit here as k gets large is going to 0. So what this is telling us is this factorial function defined here, this is getting big very quickly. It's getting bigger faster than a constant to an exponential power. So, our previous record holder for how could something get big fast was this exponential function. But that's dominated by this factorial. So somehow this factorial is growing even faster than that. And so I have two examples in the slides. I'll just go through the first one. And then the second one you can take a look at on your own, just because I need to speed up this session a little bit. So I want to evaluate this limit 1 over the square root of x squared minus 4x plus 1, and then minus x. And so basically the strategy you use to evaluate a limit like this, you want to get the square root out of the denominator. So the first step I'm going to take, if I have minus x here, I'm just going to make something called the conjugate of that by putting, it looks exactly the same, but I get a plus x. And all that's going to happen is when I multiply these together, I'll have this square root times itself, and then I'm going to get minus x times this square root, and then also a plus x times that square root. So I've got minus something plus the same thing. They're going to cancel each other out. And then in the last bit, I'll have minus x times positive x. So that's going to give me a minus x squared. And then I'll pick up this thing in the numerator of my fraction. And now I have x squared minus x squared. So I'll get rid of that. Oops, I was supposed to put a little pause here. So on the bottom, I just have the plus 1 minus 4x. And to help me make a little bit of sense out of that, what I'm going to do is just multiply the top and the bottom by 1 divided by x. And that's a safe thing to do because I'm looking at the limit as x goes to infinity. So infinity is a long way from 0, and the only time I would have trouble dividing something by x is when x is equal to 0. And so this 1 over x is going to get multiplied by x here, and then it's going to show up as a 1 over x squared under this square root sign. So what I end up with is the x squared, square root of x squared, or x squared times 1 over x squared. That gives me the 1. The minus 4x becomes 4 divided by x, and then the positive 1 becomes 1 over x squared. And then my x gets multiplied by 1 over x, just gives me a 1. And then in the denominator, I get a 1 over x and a minus 4. And now what I'm going to do, this is sort of 2 steps in one. So I can take this limit, and because this is a rational function, I can put the limit on the top and the bottom. And then also, because I have the square root, I can put this limit inside my square root sign. And then it should be pretty clear what's going to happen. When I look at this, as x gets bigger, 1 over x squared is going to get very small. 4 over x is going to get very small, but this 1 is always going to stay the same. So this is going to become 1, square root of 1. And on the bottom, my 1 over x is going to get very small, but my negative 4 is always going to stay the same. So I'm going to get 1 plus 1 divided by negative 4, which is equal to negative 1/2. And then just, this is almost exactly the same example. So here I had minus x, which I can't seem to select for some reason. Here I have minus x plus 2. But if you go through that, and I'm doing exactly the same trick, in this case, just by adding this little plus 2 here, has made the value of the limit divergent now, so it goes to minus infinity.